I told you the clay has the negative charge on the surface. If it's very fresh clay, it should have neutral electricity. So the charge should be neutral. But because of the isomorphous substitution and the other region, because of the other region, the clay becomes negative charge. So we're going to talk about the origin of this charge deficiency. What makes the negative charge on the clay surface? First is the isomorphous substitution. Isomorphous substitution, we talked about this a little bit, and there's a cation in the clay structure, right? And that cation can be replaced with the other cation, maybe with the cation with the lower valence, then the whole structure, the crystal structure will have the negative charge. So if there's aluminum in the deep side, and if this aluminum is replaced by, this magnesium, then you have one electron negative, right? You're short of one negative electron, so it becomes negative charge. And in the tetrahedral shape, there is no cation other than silicon. So the silicon can be also replaced by aluminum, then it will make the clay negatively charged. And isomorphous means the same. So when you say isothermal, means the temperature is constant. Right? Isobaric means pressure is constant. Right? Isochoric is the volume is constant, and isomorphous means the morphology is constant. Morphology is the look of the material. So silicon 자리에 aluminum 들어오는 거예요. Silicon is replaced by the aluminum.
그러면 tetrahedral.
No, in the tetrahedral shape, there's a silicon atom, and that atom can be replaced by aluminum. Then tetrahedral shape will be negative charge. 그 크리스탈이 마이너스가 된다. So, sorry for using Korean. Okay, and only minor isomorphous here. The only minor isomorphous substitution takes place in kaolinite, but these are very common in homoionite. And the other reason causing the negative charge is the imperfection of the crystal lattice. So the broken edges can make the crystal lattice negatively charged. And the third one is the proton equilibria. So when the clay is in very low pH water or high pH water, it becomes like proton and the hydroxyl ion will interact with the cation so that they replace each other. So when the clay is in the low pH acidic water, then you have high concentration of the proton, H+. Right? So then this H+ will replace the cation inside the clay mineral, so that the clay will be charged with positive proton. But in the high pH, the hydroxyl is more there. The hydroxyl ion will replace with some other things in the clay so that it becomes negatively charged. And for the protonation and deprotonation. So, kaolinite, in case of kaolinite, the particle can be positively charged on their edge when it's in the low pH environment, but negatively charged in a high pH environment. So in this case, let's say that this is the kaolinite clay, the edge, especially the edge part, can be positively or negatively charged. And this is a rare case, but the adsorption of anion can also cause the charge deficiency of clay. This one is, so you have an ion surrounded by water, or an ion only, a sole anion that can be observed on the plate surface, so that overall we can make the negative charge. But this is not common case. So in general, because of the charging deficiency, when you have a dry clay, there are always a cation because you don't have water. So somehow you have to balance the clay mineral with the electrostatically. So the cation, sole cation will be attached on the clay surface. And when it's in the water, when there's water, then the water will penetrate and separate the cation and hydrate it. It's like a sodium chloride solution in the water. So the edge can be positively charged and negatively charged, but the base generally is negatively charged. Different cation balances charge deficiency. So you may have sodium ion or calcium ion or potassium or magnesium. These are the common ions that can be found in the nature. So now we're going to talk about the water. So far we talked about the clay, and it's mostly about the dry clay, and we'll talk about the water, and then we'll talk about the interaction between these two materials. Water is we know the water is polar, but because of this polarity, it can dissolve. It's a very strong solvent, so it can dissolve many salts. And when the salt is dissolved in the water, you have to remember this hydration. The ions will be hydrated by the water, so that it will be a cluster. The sole ion doesn't move alone, so it should always it brings the other water molecules together. So when there's water in the clay, there are several interactions occurring. First is the hydrogen bonding. So the hydrogen bonding occurs between the hydroxyl ion with the water molecule or the oxygen with the water molecule. Because in the tetrahydrogen you have oxygen, and then the deep side of the octahydrogen you also have the hydroxyl molecule here. So and because this the hydrogen bonding between these oxygen atom to the hydrogen atom to water, and it makes a very strong bonding so that you have absorbed water in the clay surface. And so these 3 to 4 mono layers of water will form the absorbed water layer. And the water in this boundary has a very special property. They have special characteristics. It's not like just free water. In the free water, water vibrates, right? And they vibrate, and so that they can rotate. And when there's something like sodium or chloride, they will go there and then they can dissolve the ions from the salt. Right? And maybe they can make the ice with the making cluster with the other water molecule. So those are the free water. But now, because of this hydrogen bonding, I have to face always the whiteboard. This is the clay, and I have to face this direction. Then I don't have time to go to dissolve the other ion or the salt. So the activity itself is very lowered by this presence of the clay. So this is very highly ordered water, while this is just free water. Other is the ion hydration. Dry clay, this is dry condition, and when water is added, because the water wants to hydrate the water, the ion, the cation, so that they penetrate into the clay between the clay particle and the hydrated water. Hydrated cation or the ion. So then, because the water penetrates, what will happen? Clay swells. The volume will expand. third one is osmotic pressure. Osmotic pressure is when there's a concentration difference between in the water. There's a membrane, the water can penetrate, and one has the higher concentration, ion concentration, and the other is a dilute condition. Then water will move to make a concentration equilibrium. That's the osmotic pressure. So in between this, around the plane mineral, the cation concentration will be larger than the far side, so that the water will penetrate and to make it the ion concentration equilibrium on the ion concentration. And that is osmotic phenomena. So then we'll talk about the interaction between wet clay particles. So here, this is the basic unit, right? 221. So this is the, let's say this is a 1 molar knife, 221 mineral, and this is the basic unit. And as they step together, it makes the one particle. So this is one particle, and in the one clay particle, there's an interlayer, and between this particle, there's an interparticle space. And this is the void when we talk about the soil void. No, you can extend this, can be stepped like what, 100 or 200 of this. So this will go like about 7 or the 100 basic unit will make one clay. And there's an interlayer between these two basic units. And do you remember the crystal structure? In case of ammonium knife, because these two are bonded by van der Waals force, when there's water, one can penetrate and it can make swelling. The clay structure will swell by the penetration of the water in case of ammonium. But there's another type of clay that can, where the water cannot penetrate because of the high strength of the bonding between the vegetables. Diffuse double layer. Because the clay particle is negatively charged, so that cation concentration will increase, decrease as the distance is getting far from the surface, and the anion concentration also will increase like this. And in here, I said there's an upper water layer, right? And as you go far from the clay surface, the electrical potential will decrease. Right? The when you think about the electrical field, there's a charge, and the electrical potential will decrease to proportionally to the 1 over r, right? The distance. So the electrical potential can be plotted like this. And this is clay particle, and this is the other clay particle. And when you think this clay particle is approaching to the other clay particle, then at some point you will feel the repulsion rather than the attraction, right? And that repulsion could be very strong as you go more close to the other clay particle, which is negatively charged. And this one is also negatively charged. And there's a upper water layer, and the cation hydrated with water, and it forms the double diffuse layer. So always in the wet clay, in the solid surface there's a water, the cloud, and the water and cation cloud. That's called the double layer. And this double layer can be calculated by theory in the later slide, but the definition of the double layer thickness is that when the potential is reduced by 1 over E, this exponent, the natural number, and the thickness is defined to the distance from the surface. The thickness of the double layer on the clay surface can be calculated using this equation. This is a theoretical equation, and you have to look at the n And note here, N0 is the cation concentration, and electron charge is constant and balance. And the temperature and K Boltzmann constant is a constant, and kappa is the level of permeability. So here the ion concentration and the balance determines the double layer thickness. This is very important. So when you compare the seawater and the groundwater, which one has a higher source concentration? Seawater. Seawater is more salty. So then seawater will have the higher N than the salt of the groundwater. So it makes the K decreases, right? So the conclusion will be, when you compare the clay in the seawater and the clay in the river water, each one will have the thicker double layer thickness. This can be also related to the balance. When there is a sodium ion, same molarity, when here you may have a calcium ion with the same molarity. This is 2 plus, this is 1 plus. 1 area is half of Cebu. Does it make sense? So you have marble and area to compensate the Cebu's effect. The Cebu has 2 plus ions, right? 2 plus the charge. So when there's a calcium chloride with the same concentration with the sodium chloride, then thickness will be, because calcium is more strong, right? Okay. Particle. So depending on the pH and the ionic concentration, when you spread the clay particle in the water, it's gonna make a different fabric. And we're gonna talk about the clay fabric first. And the clay can be dispersed like this, so that the in case of dispersed fabric, absorbed water layer is like very thin, so that they are not touching each other. And flocculated fabric is when there is a positive charge at the edges, so that clay particles are flocculated like this because of the ionic positive charge, positive and negative charge difference. So in the case of flocculated fabric, you may have an edge-to-edge phase, edge-to-face, edge-to-face flocculation or edge-to-edge flocculation. And some point when the ionic concentration is very large, so the double layer thickness is thin, so they can collapse and can be obligated like this, face-to-face and shifted face-to-face fabric. In summary, electrolyte concentration, when you have an increasing electrolyte concentration or when you have increasing ion balance, then double layer recursion or double layer thickness will be reduced so that it will make it flocculated or obligated fabric. And you don't have to worry about this decreasing ion. Interaction of the clay particles. So when there's a decrease in pH, what does it mean? You have a more proton in the solution, so that it's gonna make the edge positively charged, so that you have higher chance to be flocculated. So you may develop the edge to face or the edge to edge flocculation. And decreasing anion absorption, it means that decreasing in double layer thickness and decreasing size of hydration means that double layer thickness also will decrease, so that will make the volume shrink, contraction, decreasing the double layer thickness. now we are we're gonna talk about the Atterberg limit. So this table tells you a lot. First, let's look at the sodium monoionite. And so depending on the cation observed on the clay surface, it can be categorized as potassium monoionite or calcium monoionite or sodium monoionite. Remember, the dry clay always has the potassium, the cation. So sodium monoionite, potassium and calcium, they all show the different liquid limits. And when you see here, sodium monoionite shows the highest liquid limit, 710, and magnesium and calcium has lower than that. What's the reason of that? Because of ion balance. Yeah. So because you have 2 plus, the plus 2 cation on the clay surface, you don't need much water. You need less water than the sodium monoionite. So the liquid limit means that what's the definition of the liquid limit? You turn this 25 times until it close the groove, right? Then it makes higher liquid limit means it can retain the water more while they can resist the 25 blows without failure. So higher liquid limit means they can absorb more capability to absorb water. When you look at the number, this is percent. So it can, when you have 1 gram of the clay, you can add 7 grams of water. That's huge amount of water. Cation replaceability. This one is. It's not very important, but let's just briefly discuss about that. Cation replaceability is when you have a clay surface. Let's say that your clay surface is covered by sodium ion, and when this sodium monoionite is placed in the calcium chloride solution, because the calcium chloride, there's a high concentration of the calcium chloride, some of the sodium will be replaced by this calcium. That's the capability of those exchange is called the cation replaceability. Typically, in the marine clay, because there are abundant sodium and magnesium, so that the clay are covered by, absorbed by sodium and magnesium are absorbed on the clay surface, while in the groundwater condition, the calcium and magnesium are the dominant mineral. These are the kind of each of the cation replacement. So higher valence cation can replace the cation with lower valence, and ion side with a larger radius of the cation or smaller hydrated radius will have a greater replacement power. So that when you consider this 1 and 2, you have this kind of order replacement. And the most important thing is actually the relative amount, high concentration of the sodium or high concentration of the particular cation. So, hard water softening. 한국말로 뭐라지? 연수? hard water what is? 샘물. 샘물, 단물? 샘물, 단물. So the hard water and soft water. Hard water has calcium and magnesium, so that when you mix with the salt, it doesn't dissolve the salt very much. And this hard water can be replaced and softened by adding some zeolite, which is a kind of clay. And this zeolite has the sodium on this zeolite surface. And when there is a calcium or magnesium on this hard water, this will have the higher power of the exchange. Right? So that the calcium will be replaced by the sodium. The sodium will be released into the water, so that the calcium can be removed, so the water will be softened. Just the one principle or the one method to make it softer. cation exchange capacity is about the quantity of the exchange of a cation on the clay surface. Just be aware there's this kind of a property, but it's not very commonly used in the geotechnical engineering. Swelling potential. Swelling potential is about when you add water, whether this clay will swell and how much it's going to swell. And depending on the degree of extension, it can be categorized very high, medium, low swelling. It may have a medium swelling potential, high swelling potential. And when you expand, the volume change can be rather than 30%. So let's say that there is a 1 meter of the clay layer. And when the rain comes, the clay becomes saturated. The base layer can be swelled and expand to 1 to 1.3 meters. So 1.3 meter expansion will be 30% volume expansion. When you look at the plasticity index, the PI is this one has the largest PI, and shrinkage limit is about this. And when you look at the swelling potential, three principles are these three. This is very important to remember. Presence of the monoionite in the soil. When you have more monoionite, then you have higher swelling potential. That's proportional to the fraction of the monoionite in the clay. And the natural water content must be around the plaster limit rather than the liquid limit. It means that plaster limit is pretty dry clay. So that if there's a rain coming, then the water will be absorbed more in the clay, so it's going to swell. So it will swell. So that there must be a source of water from the potentially swelling clay. Okay. So when you find these three conditions in the clay layer, then you have potential observing the swelling. And engineering application. Actually, have you heard of bentonite? No. Bentonite is a commercial name of monoionite. So they produce the bentonite from the monoionite layer, and they use this bentonite a lot in the geotechnical engineering to prevent the wall collapsing. Or when you drill the hole, as you go deeper, the upper layer can be collapsed, right? Unless you have some plastic or the steel casing. So instead of replacing the steel casing, they inject this muddy water, which has pretty high density, so that they can push the wall and keep the wall standing there. So the engineering application of the swelling clay is, one of them is the drilling mouth and the slurry. Here, to provide the earth pressure and groundwater pressure. This is the common practice of constructing the earth wall, the soil wall, the retaining wall. So they're excavating here and they're constructing the wall, prevent the wall collapsing, side wall collapsing. And with that, they actually put the concrete wall, which will be permanent wall for the building. And when you excavate, they put the slurry, bentonite slurry first. This is the ground. So as they excavate, the bentonite slurry will push this down so that they will keep the shape. They will not collapse. And after bentonite, while this bentonite slurry is keeping this wall standing, you pour the concrete mortar, and concrete mortar is heavier than the bentonite slurry, so it's going to fill up from the bottom. Then, while you're pouring this within this training pipe, as the fresh concrete is filling up, you're taking out this bentonite slurry and you reuse it. That's how you construct the side wall along the excavation site. We're gonna talk about the soil fabric from now on. And fabric is actually geometrical form. So fabric refers to only the geometric arrangement of the particle. So it doesn't tell you about the interparticle forces between them. Structure is the terminology, when you say of the structure of the soil, is the terminology indicating the geometric arrangement and the interparticle forces together. And interparticle forces are relatively important for the fine-grained soil at the low confinement. Although this is a good comment, paragraph from the Lemon-Rickman. Although the behavior of a coarse-grained soil can be often be related to particle size distribution, the behavior of a fine-grained soil usually depends on much more on geological history and structure than the particle size. So that's why for the coarse-grained soil, we do the sieve analysis, and for the fine-grained soil, we will look at the plasticity. Let's look at the clay fabric first. As you said, this is the edge and face. And there's a dispersed fabric, and aggregated fabric, and flocculated fabric, and deflocculated fabric. And dispersed fabric is like this one, so that they get dispersed with a very long distance between particles. And aggregated is when there's a face-to-face association. Flocculated is when there's an edge-to-edge or edge-to-face association. And deflocculated means that no association between the aggregate. I think you should have the same picture in your handout. Let's look at first by first. Let's just think about the thing as learning the terminology. This is the dispersed and deflocculated structure, and what will it be? Dispersed and aggregated, right? Aggregated but deflocculated. And this one is what? Edge to face, flocculated but dispersed. And this one is will be what? Edge to edge, right? Flocculated but dispersed. And this one is edge to face, flocculated and aggregated. Edge to edge, flocculated and aggregated. And this one is mixed. Mixture of E and F geometric arrangement. And deflocculated fabric and flocculated fabric, and these are the common, the idealized, it's idealized, but idealized geometric arrangement of the clay particles. Okay, why we are talking about clay? The reason that we are talking about clay fabric is when we have this kind of a clay fabric in the nature, these are formed over the geologic time. So it may be formed over 1,000 years or tens of thousands of years. And when you take a sample here to the lab, and you may press it to measure the strength, so then it will show this much of the strength. So you can retain this much of the weight. But with the same clay, you dry it and crush it and add the same amount of the water content. It doesn't form this kind of a fabric. So it means that it's really hard to mimic or simulate the same fabric in the lab, because that fabric has been formed over a very long time. So natural clay fabric is very weird phenomena. It's unique. We cannot make it in the lab, but it gives you very high strength. That's why the clay layer can sustain some certain amount of weight and the structures. Then we can talk about the granular soil fabric. Actually, granular soil fabrics are very simple. Root stacking, air stacking, and honeycomb fabric. And this honeycomb fabric is, you can see here, it has very large pores, and this is very unstable fabric. So when there's an earthquake or other vibration or shaking, then it's gonna collapse. So it will be sensitive and weak to liquefaction or earthquake or vibration. So it's called the metastable structure. Honeycomb fabric. Okay. And the granular soil, when there's a loading to the sphere particle, there's a force change. So only some of the particle carries the force, and the other particles are just supporting this force change. So the black particle carries most of the load. The remaining particle prevents the buckling of the load carrying chain. That's how the loads are carried or the transfers through the granular soil. Relative density, this one will be revisited in the next chapter, but just remember the definition here. Relative density is used to characterize the density of the natural granular soil, and that's the maximum void ratio minus E, the in situ void ratio, over the maximum void ratio minus the minimum void ratio times 100. So when the relative density is 100%, is it loose condition or dense condition? Dense condition, yes. And when it's 0%, then it's very loose condition. The void ratio will be the same with the maximum void ratio. Right? So a larger void ratio means it's loose, a smaller void ratio is dense. So as the E approaches to minimum void ratio, the relative density will approach to 100%. So the higher value is the soil is well compacted. That indicates the soil is well compacted. Okay, I think that's it. Any questions? So please read the sections of the textbook from 1.2, 1.1 to 1.9.